This is the fourth video on Chapter 39, Taylor and Maclaurin series. And this is going to be the last video. And in this video we're going to work through the solution to example 241, which is to show that the Maclaurin series for the inverse tangent function is negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1. And the interval of convergence is the closed interval negative 1 to 1. So we look at the derivative of the inverse tangent function. The derivative, as you recall, is 1 divided by 1 plus x squared, which we can write like this. Why do we do that? So we can express it as a power series. And we know that this geometric series converges if and only if the absolute value of this term is strictly less than 1. So that's why the interval of convergence is negative 1 to 1, and of course then the radius of convergence is 1. So we take this series, we rewrite it another way, and we say this is how we are expressing the derivative of the inverse tangent function. So what we want is the sum of the inverse tangent function itself. Well, the inverse tangent function is the integral of 1 divided by 1 plus x squared dx. And so it's the integral of our power series. So remember in the previous video, when we talked about power series, when we can express a function as an infinite polynomial, then we basically treat it as an infinite polynomial. So when we want to integrate this, we simply do it by reversing the power rule. So we have our negative 1 to the n, increase the exponent by 1, and divide by this exponent, the 2n plus 1. So we just find the antiderivative of each one of these terms. Now, what we also know when we do that is we preserve the radius of convergence. The radius of convergence of the series we integrated is 1, so the radius of convergence is 1. That gives us that the interval of convergence contains this set right here isn't necessarily equal to this set. We want to show that the endpoints are also in the interval of convergence. So we test those separately. We set x equal to negative 1 right here, and we simplify. Negative 1 to an odd exponent is negative 1. Negative 1 times negative 1 to the n is negative 1 to the n plus 1. This series converges by the alternating series test. This series is not absolutely convergent. So this series is actually conditionally convergent, but it converges by the alternating series test, so we know that negative 1 is in the interval of convergence. Then we set x equal to 1. When we set x equal to 1 right here, we have this series. Series n equals 0 to infinity of negative 1 to the n divided by 2n plus 1. This series also converges by the alternating series test. This series is also conditionally convergent. It's not absolutely convergent. But again, what we care about in this example is that this series does converge. And so that means that the interval of convergence is in fact the closed interval negative 1 to 1.